Hi everyone, let's continue. Last time we talked about the LU factorization. We have three methods: the Doolittle's method, Krauss method, and the Kolsky method. And in order to use the Kolsky method, the matrix A has to be symmetric, positive, definite. Okay, so today we're going to talk about different kinds of matrix. A matrix is strictly diagonally dominant if for each row, the magnitude of the diagonal entry in a row is larger than the sum of the magnitude of the other entries in that row. Okay? That is the absolute value of the AII is greater than the sum of the other entry, which is not the diagonal elements, diagonal entry, okay? The sum of the magnitude of those. Okay, so example 4. Classify the following matrices as strictly diagonally dominant. We use SDD, or symmetric positive definite. We use SPD. And please, I know, do you think P and D looks very similar? So please, when you write your homework or your exam, make sure I can be able to tell the difference of P and D. So don't put something like this. Here, I can't tell this is a P or D. Okay, so please write more clear which one is your P, which one is your D. Okay, so let's do that. First, let's check strictly diagonally dominant. So let's say this is the matrix A. So let's check SDD, strictly diagonally dominant. So what are the diagonal matrix? Sorry, the diagonal element, the diagonal entries are 5, -6, and 14. Look at the first row. The absolute value of the diagonal elements is that greater than the absolute values of the other elements, and when we add them. So this is the same as asking, is 5 greater than 3? Yes. So this row is okay. Second row is the absolute value of -6 is greater than the sum of absolute value of 2 plus absolute value of 2. That's the same as asking, is 6 greater than 4? Yes. Next, we have 14 is the diagonal elements. Is this greater than the absolute value of -1 plus absolute value of 2? This is the same as asking, is 14 greater than 1 plus 2 is 3? Yes. Okay, so yes. A is strictly diagonally dominant. SDD. So far so good, everybody? Okay, for SPD, last time we already checked it, right? First, is it symmetric? Wow. A is not symmetric. Right? You can see, this is -2, this is 2. They're not the same. So A is not symmetric. So A is not SPD. Okay? So symmetric, positive, definite, it has to be symmetric first. Right? Let me write it better. SPD. Okay, let's continue. Let me use orange color. Okay, this is our A, and let's check SDD. So let's look at the diagonal elements. Is 16 greater than 4 plus 2? So if you're familiar with that, you can omit the absolute values. Okay? So is 16 greater than 6? Yes. Next, is 10 greater than 4 plus 1? Is 10 greater than 5? Yes. Is 9 greater than 2 plus 1? That's the same as, is 9 greater than 3? Yes. So yes, A is this is strictly diagonally dominant. Okay, SDD. For SPD, first we need to check, is A symmetric? Yes, A is symmetric. Because the diagonal element is like a mirror, right? This guy is this guy, this guy is this guy, this guy is this guy. So we have symmetric. A equals the transpose of A. Next, so what do we want to check? We want to check all of the upper left symmetries has the positive determinants. Okay, so we need to check all of the upper left submatrices have positive determinants. Okay, the first one, absolute value of 16 is positive. Next, we have 16 minus 4, and 10. Well, that is 16 times 10 minus negative 4 times negative 4. Well, that is 16 times 10 minus, well, 16. So far, so good, everybody. So that is 160 minus 16. Of course, that is positive, right? And finally, we still need to compute the determinants of A. So determinants of A, 16 minus 4, 2. And we can pick any row cofactor expansion or any column cofactor expansion. But in this case, because there's no zero, so the difficulty will be the same. So if the difficulty is the same, we usually will pick the first row cofactor expansion. And the sign, the 1 entry is always positive and then negative, positive. It alternates. So that is 16 times the minor. Minor is the determinant of 10, 1, 1, 9 minus negative 4. The minor by deleting the first row and the second column are these guys. Minus 4, 2, 1, 9 plus 2 times the minor. The minor is this guy. Minus 4, 2, 10, 1. So far, so good, everybody? Okay. This is 16. Cross multiply 9 times 10 is 90. Minus 1 times 1 is 1. Minus negative 4 becomes plus 4. Minus 4 times 9, minus 36. Minus 2 times 1 is 2. And then minus 4 times 1 is minus 4. Minus 2 times 10, minus 20. Okay, so 16 times 89. This is 4 times 38, right? And this is 2 times 24. And this steps, I need a calculator. Okay, calculator, we need your help. So 16 times 89 minus 4 times 38 minus 2 times 24. 1, 2, 2, 4. So 1, 2, 2, 4 is positive. Yay! So all the upper left submissions has positive determinants. Okay? Oh, my determinant here. Determinant. So A is symmetric positive definite. So far, so good, everybody. All right. And let's continue. So for symmetric positive definite, we already know that's the prerequisite for the Kolsky's method of the LU factorization. But for the strictly diagonally dominant, we will use that conditions when we are in chapter 6. Okay, so in the later chapters. All right, let's continue to look at this example 5. Consider this matrix. So here we have a parameter A here, right? So part A, for what values of A will this matrix be strictly diagonally dominant? Part B, for what values of A will this matrix be symmetric, positive, definite? Oh, okay, so strictly diagonally dominant. So what are the diagonals? Okay, 9, 5 minus 11. So the first row we need 9 is, okay, let me do this, greater than the absolute value of the sum of the other entries. This is the same as saying 9 is greater than absolute value of minus 3 is 3. But absolute value of A is absolute value of A. This is the same as absolute value of A is less than, move the 3 to the other side, it becomes 9 minus 3, which is 6. Okay, next, we need absolute value of 5 is greater than absolute value of minus 3 plus absolute value of 1. This is the same as saying, is it 5 greater than 4? Yes. Okay. And next, we need 11 greater than absolute value of A plus absolute value of 1. Sorry, this entry should be minus 11. Okay, so we get 11 greater than absolute value of A plus 1. This is the same as saying absolute value of A is less than, move the 1 to the other side, that's 10. Because we want to satisfy all this condition. So we get absolute value of A must less than 6. If it's less than 6, of course it's less than 10, right? So this is the same as, 0 is here, 6 is here, minus 6 is here. Absolute value of A is like the distance between A and the origin 0 is less than 6. So which means is this region, right? The distance with the 0 is less than 6. So then we get minus 6 less than A minus 6. Okay, so if A is in minus 6 and 6, this is the interval notation. Okay, this guy means in. So this is the interval notation, right? And we use parentheses because we want to exclude the endpoints. If A lies in this range, then our matrix A is symmetric. Sorry, I mean strictly diagonally dominant. Okay, then part B is for the symmetric positive definite. Okay, so part B is for symmetric positive definite. Okay, if you think this shorthand notation SDD, SPD are confusing, you're very welcome to write out the whole words, strictly diagonally dominant and the symmetric positive definite. Okay, so feel free to write down the whole words. Okay, so in this case, we want to check first, is this guy symmetric? Yeah, it is, right? This is like the mirror, this is this, this is this, this is this. So this matrix A is symmetric. Then we want to check all the submatrix, they have the positive determinants, right? So first one, 9 is positive, good. Next we have 9 minus 3 minus 3, 5. What's the determinant? 9 times 5 minus negative 3 times negative 3. 9 times 5, 45. Negative 3 times negative 3 is 9. Ooh, what is that? That is 36, right? And 36 is positive. Okay. I really hope that you can try these problems before we continue. Sometimes maybe I forgot to say that, but please, before each example, I hope you can try to work on the example first. And then after we're done, you can continue to play the video and check your answers. In this case, you can have more practice, and it's good. Okay. Good. Now what's left is just the determinant of A. So let's copy down right here. We have 9 minus 3A minus 3, 5, 1, A, 1, minus 11, right? And Here, the difficulty of choosing each row or column cofactor expansion is the same, then let's just choose the first row to expand it. Okay, then we have the 9 determinant of 5, 1 minus 11 minus -3, and then, oops, the determinant of -3a, 1 minus 11. So I hope you're okay with the determinant now. This minor is -3, 5a, and 1. So far so good, everybody? Okay, now let's see. This is 9. 5 times -11 is -55. Minus 1 times 1 is 1. Minus become plus. Here, -3 times -11 is 33. Minus a. Here we have -3 times 1 -3 minus 5 times a. Okay, so -55 minus 1 is -56. 9 times -56. Calculator. 9 times 56 is 504. This is -504. Plus 3 times 33 is 99. Minus 3a. Then distribute -3a plus, oh, sorry, it's still minus 5a squared. Let's reorder it. We have minus 5a squared. How many a? -6a. And then what's the constant? Let's see here. Okay, minus 504 plus 99. Let's do it. So here, we can do 99 minus our previous answer, minus 405 equals, oh, we want it to be positive. Well, let's multiply by -1, then we have 5a squared plus 6a plus 405 is positive. So far so good, everybody? Okay. Here, so this is a parabola and it's opening up, right? This is a parabola opening up, and usually in this case, how do we determine whether there are one solution, or no solution? Okay, we check, we use the quadratic formula. Okay, and we also check the determinants. Discriminants. Discriminants is b squared minus 4ac. If discriminant is positive, we get 2 real roots. If the discriminant is 0, we have 1 real roots. If the discriminant is negative, we have no real roots. And we have 2 complex roots in this case. And those complex roots, they are complex conjugates. Okay, look at this guy. Well, the discriminant b squared 36 minus 4ac. For sure, this is negative. So, no real roots. Okay, so no real number a can make this matrix symmetric, positive, definite. Okay, but I also want to show you what happens if we actually have some roots. Okay, so here, so if we get, let's see, if we get like 5a squared minus 2a, and then minus 3 is oh, sorry, I just find a mistake. When we multiply by -1, we split the inequality. Okay, Suppose we get something like this, and then how do you solve for it? Well, first you want to find the roots. Okay, what are the roots? The 2 times 5 negative b is 2. Plus or minus square root of b squared 4 minus 4ac. C is negative, make it positive. So in this case, you see 5 times 3. Oh, 5 times 3 is actually 15. And we can fetch out the 4, we get 15 plus 1 is 16. 4 and 16 when we take square roots. So 4 and 16. When we take square root of 4 is 2. Square root of 16 is 4. So you can see we can cancel the 2. Then we get either 1 plus 4 over 5, that's 1, or 1 minus 4 over 5 is negative 3 over 5. Oh, nice number. So which means we can actually factor it. Let's check. 5a and a, and then minus 5 and plus 3a, we get 2. Yes. So this is the roots. Yes, and it matches with our roots. Okay. So which means our parabola passed through minus 3 over 5 and 1. And this is the parabola because we are looking for less than. So we don't count the endpoint. Less than is right here. So this is plus, this is plus, this is minus. So then we know we can say if a is between parentheses minus 3 over 5 and 1, then a is symmetric positive definite. Okay, so this is what happened if we actually get the quadratic equations has roots. Okay, because in our example there's no roots. But I also want to show you what happened if we get some roots. Then we actually can get some interval of a. So far so good, everybody. Okay. It is also possible that we have a one real root. In that case, we have a complete square. Then we just say if a equals to that number, then our matrix A is symmetric positive definite. Okay, so that is about SPD and SSD. So symmetric positive definite and strictly diagonally dominant. Next, MATLAB time. Okay, example 1. Find the LU factorization of the following matrix use Doolittle's method. So the syntax for Doolittle's method is brackets L comma U equals LU Doolittle's of A. So we can input the matrix and then we can do LU Doolittle of A. Then this is what you see from MATLAB. Okay? So you get matrix A and the L and the U. So far so good, everybody? Okay. And so we can after we discuss this, we can use Octave to check our work. Okay. So if we want to use Kolsky's method, then the syntax is LU Kolsky of A, right? And then you will get A and the L and U. You see L and U is the transpose of L. So far so good, everybody? Okay, and yeah, let's go back to our previous examples. Let's use Octave to check that. Okay, so first example, is this the first example? No, okay, this one is. Okay, so here. Okay, so first let's input our matrix A. So A equals 1, 2, minus 1, 2, 3, 0. Minus 3, 1, 4. Okay, so the syntax is L, comma, U, brackets equals LU capital and D capital. Do little of A. Oops. Okay, see our L and U. Let's check our work. L is 1 0 0 2 1 0 -3 -7 1 match. U 1 2 -1 0 -1 2 0 0 15. Yes, you see a match. And we can also compute the determinant. We can check that. See, -15, and we get -15. And here we can check our solution, because our solution is, so we can do B equals the right hand side vector 1 -1 0. So be careful, it's a column vector, so use semicolon. And we do A slash B. So -1.4. Oh, -1.4, that is like -7/5. And then 0.6 is 3/5. 1.2 is -6/5. You see, it matched with our answer. So when you do your homework for some problems, you can actually use MATLAB or Octave to check your work. Okay, and the Koski's method, let's define our matrix A to be now 1 -1 2 -1 5 0 2 0 14. Okay, then the Koski's method, the syntax is brackets L U equals LU Koski of A. Okay, now you see the L. So this is our L. 1 0 0 -1 2 0 2 1 3. See, it matched with our answer. And U is the transpose of L. So far, so good, everybody. Okay, and that's it for today. And so for session, so for chapter 4, we only cover this session 4.1. And then the next class we will start chapter 5. Okay, please do your homework, and if you have questions, ask me in class or in office hours, or send me an email. Have a nice day. Bye.